So finally, let's continue. Okay, so now I'm gonna, this is the part of the script I'm going to do. Create two arrays, plot both of them, and then add add a lot of decoration to the plot. Okay, so first let me do a equal to np dot range. So there are many ways to create numpy arrays. Okay, so these are different from lists. Right? In Python, you have something called lists, but in NumPy, you deal with arrays. In MATLAB, you deal with matrices. In NumPy, you deal with arrays. That's the difference. Okay, say 0 to 10. So it will create all the numbers from 0 to 9. Okay, so the last parameter is excluding. As integers, right? So you can also give step, but if you don't give any step, it's by default 1. Okay, so I'll say np dot, and you can also say d type equal to and so on, but these are some more advanced stuff which we not do here. By default, everything is float. Okay, so a range, I'll say 0 to 20 this time with the step 2. Okay, so now it will be 0, 0, 2, 4, 6, 8, and so on. Okay, so plot both of them. plt dot plot a, plt dot plot b. Okay, and then if you want to actually see the plot, you will say plt dot show. Okay, and I'm doing shift enter to run the cell. There's an error. Let's see. Oh. Okay, shift enter. There you go. I see 2 plots. Okay, this should probably be in different colors, but I don't know why they're in the same color. Are they in the same? Okay, fine. My screen is not very good. Actually, over there I can see 2 different colors. Okay, now let's see. I want to add X label, right? So you do very similar to what you do in MATLAB. X label, I say some label. Okay, so this is just index, right? So I'll just index. plt.y label is values. Okay, and then shift enter. Now you see index and values. Okay, now I can also, if I want to add legends, so for each plot I have to give a certain label. So here I will say label equal to plot A, and then label equal to plot B. Okay, and then here I'll say plot plt.legend. So now I also have the legend. Okay, and there, you can look up this this function here, parameters for that function. There, it has additional arguments for you to control where the legend will be placed and so on.
Possible to do a 3D graph on this?
Yes, I think there's a function called plot3 or plot3d, similar to So you should only use this, but plot will only do 2 dimensions. Let's see. Okay, and then also want to add a title. So here the title, some title. Okay, so those are all the decorations you can do to your plot. Any questions so far? All right, let's go further down. Okay, so let's get back to some of our material. So we talked about entropy of a random variable, right? So here, if you have a binary random variable, which will be the case for us most of the times, we'll be dealing with binary random variables. The probability distribution can be defined with a single parameter p. Right? Because if one outcome has p, the other outcome will be 1 minus p. So all you need to know is p. So in this case, the entropy of x therefore will be a function of a single parameter, right? And therefore, and then because of that, many times we'll have a special function called the entropy function. Right? It's just a function with a certain properties, and we'll use it so often so that's why we want to give it a special name. Okay, and we're going to call that entropy. So usually for a binary random variable with one of the outcomes as a probability p, this will be the entropy. H of p is negative p log to the log to the base of p minus 1 minus p and so on. Right? Everybody agree with me on the definition of entropy here? Good. Okay. Now I want to plot this function as a function of p and see how the plot looks like. Right? So at this point, any guesses on how the plot should look like? For example, what should be the entropy function when p is 0? When p is 0, is there any randomness? So what should be the entropy function when p is 0? So entropy measures randomness, right? So if there's no randomness, how much should the entropy be? 0, right? Right. So what should be the entropy be when p is 1?
1.
Is there any randomness when p is 1?
No.
So how much should the entropy be?
0.
Okay. So when p is, it's the same thing, right? If p is 0 or p is 1, it's basically the same thing, right? It's one out. In both the cases, one of the outcomes is certain. So from randomness perspective, you don't care. Okay. So any guesses about the symmetries then? Like a bell, right? So this is our guess based on our symmetries, right? So let's see how it looks like. Let's plot it. Okay, so first I want to say step. So this is I'm going to create an array of probabilities from 0 to 1, right? And then with increments of 0.01. Okay, and then create an array with to store p value. So p will be equal to np a range from 0. I don't want to include 0, so I'll start with 0.01 to 1. And the last argument is the increment. So start from 0.01, go in increments of 0.01 until you reach 1. That's what that says. But it won't reach 1, it will just stop at 0.99. Okay? You don't want to reach 1 actually in this case, because if p is 1, then this will be 1 minus 1, you're computing log 0, and you'll get the log function will throw an error. Similarly, if p is 0, again the log function will throw an error. So you don't want your p to be 0 or 1. Okay. Right. In fact, actually, when p is 0, the entropy function is actually not defined, right? According to that. But the way we will define it is, we'll say the value at p equal to 0 is the limit as p tends to 0. We'll define it that way. Okay, and the limit as p tends to 0 turns out to be 0. And you guys get to calculate that very shortly. Okay. Alex.
Sorry, no, you're not choosing the way you should. You want to
Gotcha. I think I can go bigger. Is that better?
Yeah.
Okay. Okay, so now that I calculated P, I want to calculate the entropy function. So H will be equal to minus P times NP dot log 2 of P minus 1 minus P times NP dot log 2 of 1 minus P. Okay, if you guys notice something, I'm using P, which is an array, as if it's just a scalar. Right, because all this numpy, the multiplication operator is overloaded for numpy arrays, as if it's multiplying arrays, element-wise multiplication arrays. In MATLAB, if you are doing this, you have to dot multiply, because in MATLAB treats this operator as matrix multiplication. But in NumPy, it's element-wise multiplication. Let's see. Actually, the colors here are better than multiplication. What else? Yeah, and then log2 is the integer log2 is a function which computes log2 base 2, also takes in arrays, and it returns an array of the same size. Arrays.
This one, H is an array.
Huh?
H is an
H is array, so these things return arrays, and the arrays will be of the same shape and size and everything.
So if I use, I didn't use one of my programs. I didn't use np.log. I just like log, put the bases, when I was going to log in the base. Would that affect it? Because the moment.
So I think I think Python has like so maybe a standard function logarithm. Let me see. Python log.
It's like
Right. So math is a standard. It comes with the standard Python, right? And it may have log in it. You use this one, right? It's math dot this thing. Right. So if it's inside the math package, maybe you don't need to explicitly say math because it's implicitly loaded in Python. But it's up to you. You can the same log function. No, it won't. You can. I think even for that log function, you can give NP arrays, NumPy arrays. Now the good thing about Python is it's extremely extremely object oriented, and so that means it's so heavily object oriented that it won't even show, right? Because at least in C they're like explicitly you have to explicitly say like object reference and all these things, but in Python all that is happening so heavily that it's inbuilt automatic almost, right? So that means even an array is abstracted in Python and it's called an iterable. Right, an iterable means anything you can iterate over. Okay, so log function takes an iterable as an input, and you can since iterate over arrays, you can give that as inputs. Okay, nice.
Are the arrays set size? Like once you create the array, that size?
Oh, I see. Good. So, right. Okay. This is turning into way advanced Python class than I thought it expected. Okay. So in Python, there are things called mutables and immutables. Right. So mutables are some things which can change dynamically, like list. You can increase the size of a list or decrease the size of a list and so on. Immutables are something which are which are fixed, right? So for example, a string is immutable, right? Let's say if you want to append something to a string, then you have to create a new string and copy the first string and add something else in Python. Okay, so that's how immutable means. Now NPRs are immutable. That means you cannot easily change them, right? But there are certain NumPy splicing, right, which can change individual values of an array. But if you want to, let's say, grow the size of an array, it's like MATLAB. You have to create a new array. Okay, so any rule you can apply in MATLAB where it's not a good idea to grow arrays in a loop. The same thing applies to NumPy. Okay. Anyway, so now I've computed the h function. I just plotted plt.plot. On the x-axis, I want to put t. Y-axis, I want to put h. Okay, and then plt show. Okay, and that's how the function looks like. Okay, let me put some. Never leave your plots without labels on x and y-axis. Okay. Otherwise, you have no idea what you're looking at. Okay, now here's another cool thing about PyPlot is you can actually give LaTeX inputs as for labels. So all you need to do is put an R in front of your string, and inside, if I want to type math, I can type in within $signs. Okay, so now that's a math P. So for example, I can do _1, let's say, things like that. So anything you can do in LaTeX, you can do here. Now plt y label, I'll say, for example, again, h of p. Okay. So that's the entropy, and I also want to specifically say, because I'm taking log2, I want to say it's in, I'm measuring this in bits. Okay. So does the function look like what we guessed it would be? Right. As you can see, limit p tends to 0, the entropy function is going towards 0. P tends to 1, it's going towards 0. It takes max at 1 bit. Right? That means when your random variable is a probability p equal to 0.5, that's when it is maximally random, right? That's when it has a maximum entropy. And if you're observing an experiment where you're just tossing a fair coin, then you will need on average 1 bit to describe one outcome. Right? Let's say you're tossing a coin which is just tails. Right? It has tails on both sides. Say, and you toss it 100 times. How many bits do you need to describe what's happening? What happened in those 100 times? Right? If you toss it 1,000,000 times, how many bits do you need? 1. Right? So how many bits do you need per outcome? 1 over 1,000,000, right? If there's 1,000,000 outcomes, you still need only 1 bit to represent all those 1,000,000 outcomes, right? If both sides are tails, you just say tails, and all the times, right? So as I say 1 billion, then the number of bits per outcome will be 1 over 1 billion. So as the number of outcome tends to infinity, the number of bits per outcome tends to 0. That's what entropy is telling you. Okay, if it's a fair toss, if it's a fair coin toss, then if you do like 1,000,000 experiments, then the 1,000,000 outcomes, then you need on average 1,000,000 bits to represent that outcomes, to convey what happened in those outcomes. Okay, let's say if probability is 0.25. So you just look at 0.25. Let's say some point here, maybe it's 0.7 or something, right? If it's, let's say that means there's a 3/4 chance you'll get heads and 1/4 chance you'll get tails. Let's say if you do 1,000,000 times of that outcomes, you probably only need on average 700,000 bits to represent that. That means that's not a lot, but at least you can say, but you still, you're saying 300,000 bits. Right? So that's what entropy tells you, that you can compress it, depending on the randomness. How much you can compress it depends on how random it is, or how less random it is. Right? And as the probability tends to 0 or 1, it drops quickly. You can compress it faster and faster as the p is tending to 0 or 1. And it's symmetric around 0.5. Okay. Any questions so far? Okay. So next, let's see. So far we have our code. So we have nicely formatted text and then code and plots and everything, which is describing what's going on. And then let's say you want to publish it. Somewhere you want to tell somebody. So you just go to Notebook, go to export, and then you can export it as HTML or PDF. So in my case, I tried this before. Direct conversion to PDF is giving me some errors. Maybe in your computers it won't. So I'm converting it first to HTML and then to PDF. So in this way, it didn't give me an error. So that's why I'm doing this. So if I open this is how the HTML looks like. Okay, and then I can just save it as a PDF. And this is what I want you guys to do to submit your homework or assignment. Let's see, print. Save. I'm going to save it as a PDF. Right, so now this is how it looks like. Right, so there's code and there's text and there's math and everything. Okay. And there are a few other nice functionalities you can use. For example, you can, if you're just trying to publish something without code, so you can go here and say hide all code. So it will just be, the text, math, and your plots. Right. And you can hide all outputs if you want. And, you can do all this. I would say, experiment with all this stuff. Okay. Any questions so far? All right.